Hello, my name is Dr. Ibrahimian, and in this channel I go over problem-solving strategies mainly in math competitions. This is a problem from 2024 International Math Olympiad. This is shortlisted problem A2. So here's the problem. Let n be a positive integer. Find the minimum possible value of the sum where x0 through xn are non-negative integers such that x0 through xn add up to n. So first of all, because these are non-negative integers and the sum is n, there's only finitely many possibilities. So for any given n, you can basically just write down all the possibilities and evaluate that. So it makes sense to start evaluating this for small values of n and then see if there's a pattern. But before I do that, there's an obvious assumption that we can make. Because we're trying to minimize this and these coefficients are increasing, we can assume that x0 through xn are decreasing. So x0 is greater than or equal to x1, greater than or equal to x2, all the way to xn. And because the sum of x0 through xn is n, we know that xn would have to be 0 because they are decreasing. So if the first n are 1, the last one would have to be 0. So in fact, it's probably going to be like the tail of this sequence. It's going to have lots of zeros, or at least a few zeros. So let's just start evaluating the minimum for different values of n. So let's just start with n equals 1. So the only sequence that adds up to 1 and it is decreasing is 1, 0. And then once I evaluate that, I get 1. So the minimum is 1. So n equals 2. We can look at 2, 0, 0, or we can look at 1, 1, 0. Let's evaluate the sums. The first one is 4. The second one is 1 plus 2. So 3 is the minimum of the sum. N equals 3. So we get 3, 0, 0, 0. 2, 1, 0, 0. And as you notice, I don't write down the ones that are not decreasing. And then 1, 1, 1, 0. So this one would be 9. This one would be 4 plus 2. This one would be 1 plus 2 plus 4. So this one is 6. This one is 7. So the minimum is in fact 6. Okay, so now I can write down n equals 4, n equals 5, etc. I thought if I can find a better way of evaluating this for large values of n. So for n equals 4, there aren't too many possibilities, so we can write it down. But here is one thing that I noticed once I got to a little bit of large numbers. Here is what I noticed. So let me write this down. So I have 3 zeros because I have 2 2's here. Then I have 2 1 1 and then 2 zeros. And then I have 3 1's and 2 zeros. 4 1's and 2 zeros. So these are the possibilities. So I can write this down. This would be 16. This would be 9 plus 2. This would be 4 plus 8. This would be 4 plus 2 plus 4. And this would be 1 plus 2 plus 4 plus 8. So I can evaluate these. This is 11. This is 12. This is 10. And this is 15. So the minimum is in fact 10. So the numbers are 1, 3, 6, and 10. Now you may or may not see a pattern at this point, but I do notice something that I can use in order to minimize my computation. So if you fix the first one, so let's say the first one is 4. Well, the sum of the rest of them is going to be 0. If the first one is 3, the sum of the rest of them is going to be 1. If the first one is 2, the sum of the rest of them is 2. So maybe we can use some sort of an inductive idea. So let's say I want to find for n equals 5. So what can I do? I can take the first one 5, and of course the rest of them would have to add up to 0. So the answer would be 25. Now let's say the first one is 4. The next ones would have to add up to 1. So here's what I can do. I can say this is 16 plus 2 times a sum that the sum of a similar sequence. So I have x1 squared plus 2x2 squared, etc. And this is a sequence that the sum is 1. So in other words, I can find the minimum for the sum equals 1 and then substitute that in here. So the minimum for sum equals 1 was evaluated at the beginning, so it's 1. So I get 18 here. So now let's say the first one is 3. So the first one is 3, then I have x1, x2, x3, x4, and x5. So now these guys have the sum equals 2. So I can write the sum for this as 9 plus twice something. This is minimum for the sum equals 2, which would be n equals 2. Notice that when sum is 2, these three are forced to become 0. So it's basically just for n equals 2, that because the sum is exactly 2. So now I can say the minimum here is 9 plus twice the minimum that we found for n equals 2, which was 3. So 2 times 3. So this would be 9 plus 6, which is 15. So that's when the first one is 3. If the first one is 2, then I have a sum that is, so the sum here is equal to 3. So I can look at 4 plus twice the minimum for n equals 3, and the minimum for n equals 3 is 6. So I get 4 plus 12, which is 16. And if the first one is 1, then I have something here that the sum is 4. So what does that mean? So I have x1 through x5, the sum is 4. So the minimum is 1 plus twice the minimum for 4. The minimum for 4 is 10, which is 21. So the numbers that I got are 25, 18. So these are the numbers that I got: 25, 18, 15, 16, and 21. So for n equals 5, 15 is in fact the minimum value that we get. So let's look at that and see if we can find a pattern. So for n equals 1, 2, 3, 4, and 5, we evaluated these minimums. So for n equals 1, we got 1, 3, 6, 10. So 1, 3, 6, 10, and 15. Now, you may or may not see a pattern. If you don't see a pattern, then write down the next one, and you end up getting 21, etc. Now, if you don't see a pattern here, then you might notice that this grows, but it grows kind of like polynomial. So it doesn't really grow exponentially. So you might suspect that this answer is a polynomial. So in order to figure out what polynomial it is, you can take the consecutive differences and see what the degree of the polynomial is. So this is 2, this is 3, this is 4, this is 5, and this is 6. So this doesn't seem to be a coincidence that an minus 1 is equal to n. And of course, I know that a1 is 1. So if you take that, then that means it is the sum from 1 through n. So that's the answer. So we suspect that the minimum, I'm going to call the minimum an to be n times n plus 1 over 2. So this is the claim. So the claim is minimum is n times n plus 1 over 2. So naturally, we're going to use induction for this one. So for n equals 1, we already proved this one. So we're going to go ahead and prove the inductive step. For inductive step, we established that if you want to find an, which is the minimum for n, we have to do the minimum of, we take some k, we said x0 equals k, and then we take twice a n minus k. This is what we need to do. And k could be anywhere from 1 to n. And the reason for this is that if you look at x0 squared, 2x1 squared, all the way to the power of n xn squared. This is the same as k squared plus twice x1 squared, all the way to 2 to the n minus 1 xn squared. Now, assuming that the sequence is decreasing, because here is k, the sum here is n minus k, and the tail of the sum, the tail of the sequence would have to be 0. So this would be k squared plus twice x1 squared, 2x2 squared, all the way to 2 to the n minus k, xn minus k squared. This is assuming that the sequence is in fact decreasing. And the reason is k plus x1 through xn is n. So that means x1 through xn minus xn would have to be n minus k, which means only the first n minus k can be non-zero. So the rest of them would have to be 0. So xn minus k plus 1 all the way to xn would have to be 0. Okay, so what does that mean? It means if I want to find the value for n, I have to take the values for 1 through n and put them into this formula and then compare these. These are only n values, so it can be done. Now notice that we have a claim for our ak, so we can just plug it in and see what we get. So let's evaluate k squared plus twice an minus k. This is equal to k squared plus twice n minus k plus 1 over 2. So this is k squared plus n minus k plus 1. Let's expand this. We get 2k squared plus minus n minus 1k, and then we have n times n plus 1. So this is 2k squared minus 2n plus 1k plus n times n plus 1. Okay, so we want to minimize this expression, and k ranges from 1 through n. So what is the minimum? So the minimum is at the vertex. So what's the vertex? The vertex is minus b over 2a. Now, if you look at this vertex, it's not an integer, so we can't really plug that in. But the closest integers to this are 2n over 4, which is just going down 1/4, and then 2n plus 2 over 4, which is just going up 1/4. So this is n plus 1 over 2, and this is n over 2. And these two values are going to give us the same value when we plug it into the formula. And the reason is this is a quadratic, and the vertex is here. The vertex is n plus 1 to n plus 1 over 4. And then we have to look at right here and right here, which are n plus 1 over 2 and n over 2. We go either 1/4 down or 1/4 up. One of these two is an integer. Now we take this and plug it in, and the minimum would have to be that. An becomes n over 2 squared plus n minus n over 2 times n minus n over 2 plus 1, which is, if we factor n over 2, we get n over 2 here, plus n over 2 plus 1, which is n times n plus 1 over 2. And by the discussion that we had, at n plus 1 over 2, we also get the exact value. So that completes the proof. So I will see you in the next video.